So, what we're going to learn today, everybody, is possibly one of the more important things we're going to do all year. Okay, we're going to learn the basic theory behind the derivatives. Okay, so the derivative is essentially one half of, or one of the big things we do in calculus. So it's something we're going to be doing, and to give you an idea, after today, basically everything we're going to be doing from now until the end of December is going to be derivatives of one form or another. Okay, so that's how important it is. Okay, but in order to deal with the derivative, we have to understand the basic theory behind the derivative, and essentially, when we're talking about the basics behind what a derivative is, we're really actually asking ourselves, or answering the question, how to find the slope of a tangent line. Okay? Okay? Because it ends up, that's actually, for our purposes today, and where the definition of the derivative comes from, that ends up actually being the same question. Okay, so if you take anything else away from today besides the definitions you need to know, it should be that the by definition, the slope of a tangent line is found by using the derivative. Okay, everyone got that so far? All right. So finding the slope of a tangent line. All right. So basically, let's go through and exactly figure out what the problem is and how we get to the derivative. So we're going to basically start off with just drawing any random curve here. Okay? I'll make this curve. Yeah. And we're going to mark 2 points on this curve. Point A and point B. So A here, it's x-coordinates A, B's x-coordinates B. This would be f of A, f of B, okay? Now, we figured out before, and we've seen this before, from Algebra 2 and pre-calculus and things, I can calculate essentially what's known as the difference quotient between these 2 points, and it's just essentially the slope of a secant line between A and B, okay? So if I drew a line between A and B, such a line is called a secant. Okay? And the slope of that secant line is fairly easy, right? It's f of b minus f of a over a b minus a, excuse me. So I'm going to do a minus b. B minus a. Okay, yes, you have a question?
I figured it out.
Okay, good. So that's what a secant line is, and this whole notion here, remember, can lead us to the difference quotient. If you remember correctly, the difference quotient could be defined as essentially you're doing just this, but instead of finding 2 points, you defined 1 point, and then the second point was just some arbitrary distance h away from the first one. Okay, and hence how we got that difference quotient equation: f of x plus h minus f of x all over h. Okay, that's essentially comes from the slope equation here. Now, a tangent line, okay, is related to a secant line. A tangent line is like a secant line, except instead of touching the curve in 2 places, the idea is it only touches it in 1 place, okay? So a line tangent to A might be something like this here, okay? And so this in blue is the tangent line. And what we want to eventually do here is calculate its slope. Okay? Well, what's a problem? So what's the problem with the slope equation, basically, when it comes to a tangent line?
You need 1 point.
Tangent lines have 1 point, and the slope equation requires 2. Huh. So it seems like we would have a bit of a problem here trying to calculate a tangent line slope, right? Okay. Well, so we have to figure out some way to essentially make there be 2 points when we only really have 1. Okay. Anybody have any idea how we could do that? What are things we could do?
Find 2 points on the line. On tangent line itself.
Okay, so I can use 2 points on the tangent line, and that would give me a slope, but remember, the only points I have defined are 2 on the black curve here, okay? Which are A and B. I don't know anything else on the tangent line itself, besides that A is a point on the tangent line.
Use limits.
Okay? Okay, what about limits, specifically? You're getting close there with that answer.
Well,
You just throwing it out there randomly, or did you...
You can find what's to the
Pretty much,
left
okay.
and right of that point by using limit of 10, whatever the slope is approaching. And I don't know if I explained that well.
Okay, so basically you're saying I could do something with limits as things approach A, and the slope equation that's getting very close to it, and you're on the right track. Khalid?
Well, the closer the point is to A, the closer the slope will be to the tangent line.
Ah, good. So maybe if we took what you were just saying and what you were just saying and put them together, we would actually get the slope of the tangent line. And that's exactly what we're doing. Basically, how to find the slope of a tangent line is I'm going to take this point, basically this point B here, and I'm going to shrink the distance between A and B down until B and A are practically equal. That is, they lie right on top of each other, okay? And so essentially I'm going to make the difference between A and B arbitrarily small. I'm going to do that using limits, okay? The idea being, remember, a limit is not getting something to be directly equal to something, it's just getting it to the correct ballpark, essentially. As long as I'm close enough, I can essentially figure out the slope of a tangent line this way, okay? And that's exactly what I do. So from this right here, to calculate out that tangent line, okay, we're going to switch things over, and instead of using the, I do not want to use this color, hang on. Let's try to keep things the same as they were before. Okay, so here's my point A, okay, and I'm going to mark point B up here as well. So this is B, f of B, and this is A, f of A, if you will, okay? I'm going to take this distance here and shrink it, okay? Okay, so I'm going to shrink it so basically they lie right on top of each other, okay? One way I could think of doing that is by rewriting the slope equation into the same form as the difference quotient. If you remember correctly, the difference quotient basically reads, the dq if you will. I should write out difference quotient. This is the first time. If I tell you, first time you write something, you should write it fully out. Okay. Kind of the difference quotient applied in this case here. Remember, it's f of x plus h minus f of x all over h. What I could do here is I could equate all the pieces of the difference quotient to the slope equation for this secant line up here. Basically, f of x plus h is the same thing as f of b. Okay? F of x can be thought of the same thing as f of a, and then h can be the difference between b minus a. Okay? Everyone see how that works so far? Made straight substitutions between the two equations. And now what I can do here is, the idea is, I can figure out the slope of the tangent line, or of a line tangent to this curve at point A, by shrinking the difference between B and A, by making it go to 0. And that's where the limit comes in, okay? I can rewrite all of this, okay? And basically make the, oops, hang on one second, okay? I can now calculate the slope of a tangent line at A by taking the limit of the dq as h goes to 0. So what does that become? It would become the limit, h goes to 0, of f of x plus h minus f of x all over h. Okay? That's essentially what I'm doing here. okay? Remember, f of x is a, f of x plus h is the same thing as f of b, okay? H is the difference between b and a, and what I'm doing is I'm basically making that difference 0, which means I'm drawing b to be arbitrarily close to a, okay? Everyone see that so far? All right. We've seen this before. In fact, we saw that on several homeworks last week, didn't we? That same exact sort of situation, which is repackaged in different ways. Okay? There's a reason for that. You didn't know it, but you were actually calculating what the derivative was for those cases. This thing right here, okay? I'm going to make that look more like an x. And I'm going to post these notes online, of course, so you can reference them at your leisure. Okay? This thing right here is called f prime of x. And f prime of x is the derivative. It's actually something called the first derivative. Okay? Okay? And so what it's doing is it models how you find the slope of a tangent line. Okay? Any questions on how this works? Okay? Does everyone get the basic idea of what I'm doing? I'm essentially finding the derivative. Okay? I'm finding the slope of this tangent line by, instead of treating it like a regular secant, I'm treating it like a regular secant line, but instead of having 2 points that are far away, I'm essentially making the points one on top of another. Okay? They're so close together I cannot tell the difference between them. Okay? They're so close together that the 2 points common difference is 0, basically. Okay? By doing that, that lets me cheat the system and take something where I have just 1 point and be able to treat it like it's 2. Okay? Which is exactly what I've done here. All right. We've all got this down here. We'll go ahead and write out formally what the derivative is. Okay? Or the definitions, the working definitions we'll use by. I mean, obviously, there's more to it, like let f of x be a continuous function, for an interval from a to b. Then the derivative at c is defined as something or other. Okay, we don't necessarily need to be that formal with it, but we will have a basic working definition. Okay, so essentially the definition of the derivative. Okay, there's actually 2 of them. Okay, you all right?
Yeah, sorry.
Okay. There's actually 2 definitions of the derivative that we use. Okay? The first one is the one I just showed you. That's the derivative for a function. Okay? And what it's written is that f prime of x is equal to the limit, h goes to 0, of f of x plus h minus f of x all over h. Essentially, it's the limited difference quotient. That's one version of the derivative. There's another version of this, okay, that's very similar, and when you go look at it, you're like, oh, it's exactly just kind of the slope formula. And it's the derivative at a point. Okay? And that formula is at a point A. Excuse me. At a point x equals A, we'll say. Okay? And how that formula reads is that f prime of A is equal to the limit as x goes to A of f of x minus f of A all over x minus A. Recognize that? What's that look exactly like? It's the slope formula, right?
Yeah.
The only difference is I'm taking the limit as the 2 points, again, go right one on top of another, okay? These have different functions or different reasons why you use these. Primarily, the answer for the one on top comes out as a new function, okay? So I get an equation that comes out of this when I apply this, okay? The bottom one gives me an actual numerical answer, okay? So that is, when I apply the bottom one to a system, I get an actual value that's the slope at that point, okay?
Wait, why do you want to find a derivative again?
because it answers the question of how to find the slope of a tangent line, okay? Which is what we're after. And as you're going to see here, once we get this down and we start looking at applications, there are many uses of the derivative, okay? Anybody in here in physics? Those like speed, yeah, speed, velocity. In fact, the derivative of position is velocity. The derivative of velocity is acceleration. Okay, so those are all uses of the derivative. In fact, all this was originally came up with to answer those questions in physics. Isaac Newton figured this out in the 1600s. So anyway, any questions about these right here? The other thing to remember, guys, okay, about this is if you remember, okay, I said last week there were a few things that you absolutely had to know for the AP theory-wise. That is, theorems that will and do appear in the AP. We learned one last Saturday, or Friday or Saturday, whatever day it was, the intermediate value theorem, the IVT. Okay. The next big theorem that we have to have is both definitions of derivatives. The derivatives. That is, you need to know both of these exactly as they are, essentially. Okay? And there are certainly questions in the AP where they essentially just ask you for this. Or, one of my favorite ones is, they'll show you this god-awful limit. You'll see this terrible, awful-looking limit, and you'll be like, oh, goodness gracious, how do I calculate this thing? Well, you look at it a little closer, you realize it's actually just one of these two derivative formulas. And it becomes a cinch. Especially when you learn ways to calculate derivatives without using these, okay? Basically without using this definition, okay? Any questions about the definitions? All right, let's look at some examples of where you would use these, or how these get used, okay? So, examples. Our first example is going to be probably a classical problem that a lot of people have trouble getting correct, okay? And that's because while the derivative has tons and tons of uses, its primary function, remember, is to calculate the slope of a tangent line. And for some reason every year, and on every test from now until the AP I give you, there'll be a question on there saying, find the slope of a tangent line of a certain function, and the answer is essentially, take the derivative of that function, okay, and evaluate it at whatever point in question, okay? So, that's a standard question we will see over and over again. So here our first example would be, find the slope of a line tangent to the function f of x equals x squared minus 2x plus 7, okay, at x equals 3, okay? And so we're going to use the definitions we just learned. Now, which one do you think I should use here? The first definition or the second?
Second.
Why the second? What have I been given?
So, yes.
A point, okay? Because I've actually been given a point here, in this case x equals 3, I should use the definition of the derivative that uses a point. That would be the second one, right? The second one I wrote up there. So let's use it. That second one, to remind you, is that f prime of a is equal to the limit, leaving off the limit, don't forget to write the limit, as x goes to a of f of x minus f of a over x minus a. So, what's a here going to be? 3. We've got f of x. What's f of a going to be? All f of a is going to be is f of x evaluated at 3. So that's going to be 3 squared minus 2 times 3 plus 7, which indeed comes out to be 10. Okay? Because it's 9 minus 6 plus 7. Okay, so 16 minus 6.
How do you know A is 3?
It's the point we're given. That's the only thing a could be. Okay? So now that we have all that, we can put these pieces into our formula. So f prime of 3 is going to be equal to f of x, which is x squared minus 2x plus 7, minus f of a, which we figured out was 10, all over x minus a, which is x minus 3. Okay? So that's the all the pieces there. And hold the phone. What did I leave out? The limit part. Goodness gracious. I'm tired. There we go. Okay? Well, let's go ahead and clean up and solve this limit. What's it going to come out to be? On top, what's going to happen?
X plus 1, x minus 3.
Okay? So it comes out to be x plus 1, x minus 3. Before then, I would end up with x squared minus 2x minus 3, right? We'll do that first.
But so did you end up going from the second definition to the first definition after you got your answer to the first definition?
No, I'm just using the, no, I just went in with the definition that uses the point, okay?
Do you mean to write a equals 3 up in the problem? I don't get how you're getting a to equal 3.
Okay, A in this thing is just a point, okay? So what are our points defined? So the only point I have defined for my function is that x is equal to 3, right? So in here, you'll often see it written this way. That's why I'm kind of copying it here. Here, the a in question is just that defined point, which is 3, okay? The x here is kind of the same x as you would see in like the point-slope formula, how you have x minus x of 1, okay? Where you have an x that doesn't mean anything. It's just a placeholder, essentially. It's just the x that is the variable in the problem, okay? Does that make sense?
Right, that thing simplifies, right?
Yeah, we simplify, okay? Okay, and as we simplified, somebody already figured out it was, what was it?
X plus 1.
X plus, x minus 3 times x plus 1 over x minus 3.
Yeah.
Okay, those x minus 3's obviously cancel, and now I can take this limit here and get my answer as 4. So the slope of the line tangent to x squared minus 2x plus 7 at the when x is equal to 3, the slope of that tangent line is 4. Okay? Any questions about that?
That's it.
Okay, that's it. That's the slope of that tangent line. Okay? And this is how it works for a point. We're going to look next to see how the function definition of it works. Okay? And then why that's a useful way of doing things. Okay? And then why one way, when you would do one way and when you do the other and things like that. Okay? But this is how calculate derivative. There are faster ways to do this, by the way. In fact, I can confirm right now by just looking at the function and knowing a better way of doing these things that the answer was indeed 4. Okay? And we're gonna go over those ways next week. But for now, this is how these things are done. So 4 is indeed our answer. Okay. Any questions so far about this? By the way, 1 second. By the way, one thing that always ends up being the case, if the derivative exists, the bottom here will always be a factor of the top. Okay. If the derivative exists at the point. Okay. Remember, derivatives are using what? What do they use throughout all this process? The what? Limits, right? So for a derivative to exist, the limit has to exist. So the limit doesn't exist, guess what doesn't exist? The derivative. Okay. You have a question?
Yes, sir. If you find the derivative of a function, can you just put in a point?
Yes, you can.
Okay.
And we're going to look at that right now, okay? And that's what this over here is explaining to an earlier class. So let's look at a different example, okay? This is one where I'm going to find the derivative as a function, okay? So the answer I get from this is a whole new, essentially, function, okay, of x. So we'll start off with calculate, okay? We'll start off with f of x be equal to, we'll keep it simple and keep it at x squared. We'll do x squared plus 3x minus 4. So we want to calculate, this is calculus after all, calculate f prime which remember just means the derivative of x. Okay? This time there's no point defined. Okay? So there's no x equals 5, or let a be 2, or anything like that defined here. So when there's no point given to you, you're going to go with that first definition we saw, the one that we derived in class today. Okay? So that first definition, if you remember, is the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, we've got f of x. We know h is just h. The only thing we're missing here is f of x plus h. So go ahead and just figure out what that should be. All f of x plus h is remember this function with the x's replaced by x plus h's. Okay? I cannot tell you how many times I've seen students mess this up because they're not about to do the step I'm going to take, which is simply write out what f of x plus h is. Okay? That's going to be x plus h squared plus 3 times x plus h minus 4. And we go ahead and clean that up. X plus h squared is going to be what?
X squared plus 2xh plus h squared.
Then this would be 3x plus 3h minus 4. Now that I've got all the pieces, I can go ahead and calculate using the limit definition. So prime of x is the limit as h goes to 0 of x squared plus 2xh plus h squared, okay, plus 3x plus 3h minus 4 minus this guy right here. So when I put it in, it'll be x squared minus 3x plus 4. Okay, when I work it all out. This is all over h. What's going to happen here?
Crosses out.
A bunch of stuff cancels. Like what? What cancels out first? Okay.
X squared.
The x squares cancel.
4s.
The 4's cancel. And the
3 x's.
3x's cancel. Now what can I factor out of that top there?
The h.
The h. So we'll go ahead and do that. That give me 2x plus h plus 3 all over h. What's going to happen to these h's? They cancel.
Oh, where'd you get minus x squared minus 3x plus 4? Wait, why?
Okay. Our function is x squared plus 3x minus 4.
Right.
I put it in there. What's in front of it all?
Yeah.
A minus sign. So that's why it becomes minus x squared minus 3x plus 4. Okay.
Word.
If it helps, don't do what I did. Just take an extra step, put parentheses around it when you stick it in, and then distribute that minus sign. Okay. And you'll get it every time. Okay. But we get to right here. I can actually take this limit now, can't I? What happens when I put 0 in for h now? What am I left with? 2x plus 3. So what I've done there is found an equation, okay, for the derivative, or for this function, basically an equation in which will model the slope of a tangent line for any point in the original function here. Okay? So now that I've got this down here, I come through here and say, okay, I know f of x is equal to, what was it, x squared plus 3x minus 4. And that I just figured out f prime of x is equal to 2x plus 3. So now if I said, okay, what's the slope of f of x at x equals 4? Okay? All I have to do is just plug 4 into this thing, and that gives me my answer. F prime of 4 equals 2 times 4 plus 3, which is 8 plus 3 or 11. So if I need to do something else, let's say at x equals minus 16. Well, minus 1. We'll do minus 1. Minus 16 is a little big. Well, that'd be f prime of minus 1, which is 2 times minus 1 plus 3, which gives me 1. So now I have an equation that gives me the slope wherever I want it. Okay? Now, you might be asking, well, Mr. Dowell, this is nice because now I have this equation I can use for the entire function, whenever I want to. Why don't I just do this every time? Well, look at what I had to write out for it just being x squared plus 3x minus 4. What if this thing was like x to the 5th minus 7x to the 4th plus 3x to the 3rd minus 2x squared plus 8x minus 17?
You wouldn't do that to us, would you?
I wouldn't do that to you, but notice how big that would be. Anybody in here want to do the fifth, quinomial? I guess that'd be the correct word for it.
No, thank you.
No, you would be crazy to do it, right? Okay, I mean you could do it if you know your Pascal's triangle. You could work it out, but still, that's a really big thing to expand, and you're left with this huge thing, and it just becomes a pain in the butt. Well, however, if I used the point definition, okay, I can just plug everything in and know that the bottom is automatically a factor of the top, and clean up that way and get my answer really quickly. Okay, so there are benefits to doing it both ways. Okay, all right. Any questions about this so far?
No, we do.
All right. In that case, bye-bye, everybody.